you've heard me use the term molar solubility. What is exactly molar solubility? Well, the definition of molar solubility is the maximum number of moles of any particular substance that may be dissolved in 1 liter of solution. So I put a substance into 1 liter of water, and how many moles of that substance dissociates. So we can describe molar solubility mathematically looking at the equilibrium concentrations from an ice table. So here we have magnesium hydroxide, which is a weak base. It's the active ingredient in milk of magnesia that you drink when you've got an acid stomach. It's a very weak base, so it's just like it is a sparingly soluble salt. And however many moles, the value of X in the ice table that dissociates into its products, and in this case its products are magnesium ion and hydroxide ion, however many moles of magnesium hydroxide dissociates, that's its molar solubility. And its molar solubility is always equal to X. So in the equilibrium line of our ice table, we have plus X because we get 1 mole of magnesium ion every time 1 mole of magnesium hydroxide dissociates. You can tell that because the understood subscript of magnesium here is 1. And then we also get 2 moles of hydroxide ion every time 1 mole of magnesium hydroxide dissociates. And you can tell that because the subscript of the hydroxide ion is 2. So that is going to be 2X. So at equilibrium, X, the value of X, is the number of moles of magnesium hydroxide that dissociates. It's the molar solubility. Molar solubility always equal to X from the ice table. So now that we know what molar solubility is, we can calculate the equilibrium constant, what we call the solubility product for a particular substance, if we know what its molar solubility is. In this case, the molar solubility of silver chromate, this substance right here, is equal to 1.3 times 10 to the minus 4. And all you have to remember here is that 1.3 times 10 to the minus 4, the molar solubility of silver chromate, is equal to X. What we want to do now is we want to go ahead and calculate the solubility product, the KSP, and we do that based on the ice table. So the first thing we do is we write the reaction. That is always the first step, and that is to write the reaction that drives all of the mathematics that we use. So we have 2 silvers and 1 chromate. That's a solid. We're going to go ahead and put it in water, and you know this is a sparingly soluble salt. Most silver compounds are, and it'll dissociate into 2 Ag plus in aqueous solution. Not completely. Remember, I'm only getting a tiny bit of these products. 1.3 times 10 to the minus 4 is equal to X, and this is going to be chromate, CrO4 2 minus. Just a little bit of this stuff. Now, in our ICE table, if we were to put that together, we have some mass of this to start with, and we don't know its concentration. Not in any way that would help us with the molar solubility. But if we can measure the initial concentration of silver ion and chromate ion as 0, and then understand as silver chromate dissociate, every time 1 mole of silver chromate dissociates, I get 2 moles, 2 times X of silver ions, and I get 1 mole or 1X of chromate ions. I add everything up, and here we don't really care. We have a little bit less mass, very tiny bit less mass. But over here for the product, we get 2X and we get X for the chromate. So 2X for silver ion and X for the chromate ion. And we realize that the value of X is equal to the molar solubility. So we're going to go ahead and calculate, put together an equilibrium constant expression, and we know that that's going to be KSP is equal to the concentration of silver ion, and the concentration of silver ion we've computed with our ice table to be 2x. We need to square the silver ion because the coefficient of silver ion is 2, so that means we need to square the 2x. And then we also have chromate ion, CrO4, 2 minus, and its coefficient is 1, so we only have the 1x, and so that's also x to, or chromate to the first power, and x to the first power. So since we've got 2x squared, that's going to be 4x squared. We go ahead and we square the 2 along with the x times 1 additional x for the chromate, and so that becomes 4x squared times x, which is equal to 4x cubed. Now, since we know that the KSP is equal to 4x cubed, and we know the molar solubility, it was given to us in the problem, is 1.3 times 10 to the minus 4. All we have to do is plug that value into this equation. So that's going to be 4 times 1.3 times 10 to the minus 4, and we have to remember to cube that term. And we do that, we get a KSP that's equal to 8.8 times 10 to the minus 12. And that is our solubility product, our KSP. That tells us this is a heavily reactant-favored equilibrium, that most of our solid will exist as solid silver chromate, and we'll get very, very few of these product ions. So that's our KSP.